Question number 5. So this start off as a fixed essay question. So for 4 marks, you are supposed to compare the basicity of phenylamine, so the NH2 bonded to a benzene ring. Then you compare with ethylamine, CH3, CH2, NH2. And you're supposed to compare with, this is a strange one, this is a 4-nitrophenylamine. So this is position 1, 2, 3, and 4. You could also think about 1, 2, 3, and 4. So these two are pretty common in the essay. So the other one being ammonia. So this thing is pretty new, but doesn't matter. So we can think of NO2 as an electron withdrawing group. You know it's an electron withdrawing group because you have it in your data booklet that it is actually 3 and 5 directing as part of what electron withdrawing group tends to direct substitution position onto. That's how you know it's electron withdrawing group. Anyway, basicity. What is basicity to do with? So I'm going to start by explaining first. So if I explain first, basicity is to do with how available is your lone pair on the nitrogen. Is the lone pair of electrons on the nitrogen to do what? To accept H+. Now if we think about phenylamine, well, this is also phenylamine, so we can compare a phenylamine system like that. So feel free to always draw some diagram in order to prove your point. So the lone pair there get delocalizes into the system. Lone pair on nitrogen in the phenylamine delocalizes into the benzene ring. For the nitro group at position 4, this gets further delocalized. The lone pair gets further delocalized. The lone pair on the nitrogen of NH2 gets even more delocalized over the NO2 group, therefore less available, meaning to say the lone pair on the 4-nitrophenylamine is actually less available to accept H+ than just phenylamine. So far I've just drawn phenylamine on top there. What I'm going to draw now is the effect of the nitro group. So hopefully it will become clearer. So what I'm talking about is, if this is NH2 drawn like that, and you have NO2 group, which is actually drawn like this, the nitrogen with 4 covalent bonds, that's why it has a plus charge, and this oxygen with single covalent bond, that's why it's a minus charge. What happened is this lone pair can get delocalized. So if I draw the cocoon structure, I could delocalize it like that, and this could go there, and this could go here, and this could go there. So I can draw my resonance structure. Resonance is basically the different forms of this thing here. So when I form this double bond here, I become a plus. Obviously we don't like to destroy our aromaticity, meaning to say we don't like to have the benzene ring not being benzene ring. Overall, the +1 cancel the -1, the +1 +2 cancel the -2 charge. This is what you call resonance stabilization. Resonance stabilization is basically delocalization. Whereas previously, you could just delocalize the lone pair into the benzene ring. Here you have the nitro group at position 4, very conveniently set up, where all of these are actually these are trigonoplanar. This is not exactly trigonoplanar, it's trigonopyramidal, but to some extent, the lone pair can actually get delocalized over the benzene ring as well as the nitro group. That's why I said here is this extra point, and this is probably what will catch out a lot of students who are just prepared for the most common essay. They don't think about what is the effect of the NO2 group, which is more electron withdrawing, and therefore it makes the lone pair on the nitrogen even more delocalized into the benzene ring via the NO2 group, and therefore it's actually less basic than just the phenylamine, which delocalized over the benzene ring only, whereas this it moved it further into the nitro group there. Of course, then you have to complete the essay by comparing ethylamine as well. So for ethylamine, the CH3CH2 group is electron donating by inductive effect. So that is electron donating by inductive effect. Inductive effect is something you have learned in alkene chemistry, in AS chemistry syllabus. If you don't believe me, you can have a look under alkene chemistry. That's the mention of this name. Inductive effect stabilizes carbocation, and here it's not stabilizing carbocation, but it's just pumping electron density to the nitrogen, and therefore making the lone pair more available to accept protons on the nitrogen, more available to accept protons, more available. Okay, therefore going back to your trend, if you want to think about the most basic, it is going to be the one where the lone pair is most available, which is going to be the ethylamine. So CH, well, I don't need a formula, just need to provide the name, I guess. Ethylamine, followed by phenylamine, and then followed by the 4-nitro phenylamine, which actually managed to delocalize the lone pair on the nitrogen even further into the nitro group, being an electron withdrawing, as I mentioned, via delocalization of the electrons. It's 4 marks because 1 mark for the trend, 3 marks for the explanation. Most students should be able to get these 2 correct. This is probably the harder one to explain unless you think about the structure and bonding of nitro group. Question 5, part B, is about synthesis. So this is the typical synthetic procedure. You're starting from the phenylamine, 4-nitrophenylamine, and you're forming something which is Q, and then you get this last step where you get the azo dye. The azo dye consists of nitrogen-nitrogen double bond. Then you start it off from that phenylamine back bond, and you have like a phenolic group. Basically, you're doing a electrophilic substitution on a phenolic group. When you do a electrophilic substitution on a phenolic group, the phenol directs electrophilic substitution at position 2, 4, and 6, or I can imagine as 2, 4, and 6, just like that. It could be there, it could also be there. This is what is given as R, so meaning to say what is going to be my Q. Well, I need it to be diazonium before I actually could do any diazotization. So this is the diazonium chloride, and to do this step 1, this is basically forming diazonium, and there is actually something that people call diazotization, and this thing is actually formation of azo dye. And to do the formation of azo dyes, you need to do electrophilic substitution, because that's what essentially happens. This is the mechanism for what happens when the phenolic group directs substitution on these positions and attack that nitrogen, giving you the 2 electrons back to that nitrogen with the positive charge. So all in all, you need your other reactant to be these phenolic substituents. So something that has the phenol back bond, and what you have done is you have substituted out these hydrogens with these nitrogen there. Okay, so deduce and draw the structure for Q. I have just done that. It's this diazonium chloride. Whatever you do, do not bond the chloride to the nitrogen, because the nitrogen there is a second period element. Even O level or IGCSE year 9 student know that nitrogen, being a second period element, cannot have more than 8 electrons in the outer shell. Here we have 4 covalent bonds with 8 electrons. You can't form 5 covalent bonds with elements from the second row of the periodic table. So part 2, so that was part 1. Part 2 of this question is reagent and conditions. So step 1, as I said, is forming the diazonium. To do that from the phenylamine, you would typically need dilute HONO, which is nitrous acid. You could call it HONO, or you could just call it HNO2. It's the same thing, and this has to be reacted with dilute HCl. They say reagent and conditions, so do not forget your conditions as well. This one has to be kept cold. 0 to 5 degrees Celsius is required to keep this thing. Anything above 10 degrees Celsius will be enough for the nitrogen to escape as nitrogen gas, meaning the whole thing would decompose. If you don't keep it as diazonium, you don't get the azo dyes forming. This is azo dyes. It will be brightly colored, whereas these things are not colored at all. Onto the step 2. Step 2 is basically forming this thing here. So funny story is, you know what's the funny story? Funny story is I've got to draw this in here, and they have given me a space there to write. I don't know why they give me the space there to write. Instead, what I'll do is I'll draw. I don't know how to write this as my reagent. This has to be the reagent, because that is where you direct the substitution. So it could be there, but it decides to form this particular azo dyes at this position. Electrophilic substitution loses the H there. Kick out the Cl minus, you kick out HCl, but at the same time you get electrophilic substitution mechanism there. Okay. So when I say I don't know what to draw there, because they're giving me a written space, not too sure how to write that down in the written space. But if I were you, I would just draw. It's a lot easier to just draw. Okay, so that has to take place with that. And what happened is sometimes people use aqueous NaOH because they want to make the phenol a little bit more activated. You can deprotonate phenol, and it will make the benzene system even more reactive towards electrophilic substitution. It will attack these much better. So you will warm up. You will warm from 0 degrees Celsius to room temperature. So as you warm it up slowly, basically you keep that thing stable. You keep this thing that was stable at 0 to 5 degrees Celsius or 0 to 10 degrees Celsius, and then as you put in the phenolic component in the presence of base, it's going to be highly activated. It attacks this particular electrophile on this nitrogen. In doing so, it'll kick out that hydrogen there and kick out the steamy white film HCl, and you just let it warm up slowly from that low temperature to room temperature, which is 25 degrees Celsius, without heating whatsoever. Component C seems to be much longer question, but what do we have in component C? We started out from this thing called methyl benzene. So we have a methyl group on a benzene, and we have E, which we don't know what it is, and we have F, which we don't know what it is, and we have step 3, which we know what it is, but here we have NO2, here we have CO2H, and here we have Br. So what do we see here? We see that we have done a couple of things going from here to here. First of all, this is our methyl group. Now it becomes a carboxylic acid. We can think about oxidation of alkyl side chain on a benzene ring. So alkyl side chain of a benzene ring will get oxidized by acidified KMnO4 to give you benzoic acid. So alkyl side chain bonded to benzene. However, that is not the only reaction that's happening. We could also see there's nitration, which is a electrophilic substitution, not an oxidation, not a redox there. We also see another electrophilic substitution, which is Br. So there's bromination, halogenation. Don't forget that these are name of reactions. but the type itself is substitution, and the mechanism itself has a name. It's called electrophilic substitution mechanism. Should probably write it down somewhere so that you're not confused between what is type, which is what AS introductory organic chemistry we have taught you, and then this is, I can't even write properly, electrophilic substitution. Okay, so here in this question, the key is really the order of doing things. Do I want to oxidize first, or do I want to nitrate first, or do I want to brominate first? That's the important question. If you see carefully, the CH3 group directs substitution to position 2, 4, and 6, and this is given in the periodic table, which group do they direct on. If I oxidize first, if I do this first, then I'll get CO2H and like that, and that would direct to position 3 and 5. This is stated in the data booklet as well. The CO2H direct 3 and 5. I don't get any of my substituent at position 3 and 5 relative to the CO2H, meaning to say I do not want to convert to I do not want to oxidize first. That's my point. I do not want to do number 1 first. Instead, what I want to do is I probably want to do nitration first. So what I suggest is do nitration first. Then what happen is I will get the NO2 at position 2, and I still have the CH3 there. After that, what do? I don't want the benzoic acid first, because if I oxidize now, then I'll get substitution at position 3 relative to that, and this NO2 might also direct there. So I think the next best decision really is to direct it to position 4. So that is just to, based on the CH3 directing it to position 4, and the NO2 will direct to position 3 and position 5 relative to itself. If I go to green color, it will be the CH3 group that direct it to position that and position that and that, but that is already occupied, so instead it goes for these positions. So number 2 is going to be the halogenation there. Okay, so if I just copy paste that, so we're going to do the halogenation, the second bit there. So that is just BR, and then I'm going to do oxidation for the final step there. Hopefully that makes sense to you entirely. Let me just put that in the bracket. Does that work out all right? Yep, that looks all right. Let me put that in the bracket. Oops, nope, that doesn't look all right. Just make it a bit bigger. Nope, that doesn't look all right. Try that again. Yep, that looks better. So what we say is this is oxidation, and this is electrophilic substitution. This is also electrophilic substitution. Now going back to the original question, they say give the systematic name of compound G. So this is the benzoic acid. This is the benzoic acid because it is a 1-carbon carboxylic acid bonded to a benzene ring. This is a nitro group. This is a bromo group. The benzoic acid is the number 1 important carbon there, bonded to the benzene ring. So I've got 2 nitro and I've got 4 bromo. So between the nitro and the bromo start with a B. The N there is well, actually, hang on, give me a minute, because this is not halogen. So this is based on position. So it has to be 2 nitro, 4 bromo benzoic acid. So the official name there for this question, 5C, is it 5C or 5D? 5C part 1, G is going to be 2 nitro, 4 bromo. Since I'm not comparing halogens and halogens, I don't care about the alphabetical order. Okay, so this is just based on the position. So 2 nitro, 4 bromo, benzoic acid. So in terms of the substituents, we want the one with the lower alphabet to come first. So it's 4 bromo and 2 nitro. In terms of the alphabet, B comes before N. So question 5, C part 1, the systematic name for G is going to be, what did I say just now? 4 bromo, 2 nitro, benzoic acid. For part 2, suggest the identities of E and also F, and we already did that based on the discussion about the order of substitution earlier. So what order of substitution matters, because it's all about the directing effect, where you're going to put the substituents, and those are all information given in the data booklet. For part 3, so 2 is already shown above. And then for part 3, suggest reagents and condition for each of the step 1, 2, and 3. Well, actually, even though I put down these 2, 3, and 1, they are not the exact step as mentioned. The exact step given in the question is step 1, this is step 2, these are step 3. The one circle is basically what I've written down as the list of reactions that we have to do. So for this step 1, we have to do nitration of a methyl benzene. So for that we need concentrated nitric acid as well as concentrated H2SO4. And since we are nitrating benzene or methyl benzene or alkylated benzene, we need a reflux of 50 to 60 degrees Celsius to make it happen as well. For step 2, we are doing halogenation. We are trying to add bromine substitute bromine in place of the hydrogen on the benzene ring. So here we need acid catalyst. We use FeBr3 as your catalyst. Very important that you mention this. And then Br2 as your reactant. As a matter of fact, I should probably put catalyst before my reactant. So I need the Br2 as my reactant. I should probably mention that I need liquid bromine as my reactant and not aqueous bromine, because with anything in terms of benzene itself, you need a concentrated source of the halogens. What better than the liquid itself? FeBr3 catalyst. And again, electrophilic substitution on the benzene ring is not as easy as on the activated phenol or phenylamine. Step 3 was the last step, which was the oxidation of the alkyl side chain of benzene ring. This one is very specific, has to be using the acidified KMnO4, or you can say acidified MnO4 minus, and don't forget to reflux it as well. So dichromate 6 will not work for this particular oxidation. That's the end of that 13 mark A2 aromatic chemistry.